Hi, everyone. So today's lesson, technically the title is Permutations from the book. We're going to be looking at permutations and combinations kind of side by side because I think it makes more sense to look at them next to each other and understand the difference between the two. So you've actually already worked with combinations this year when we did Pascal's triangle, but I don't know that we talked a whole lot about what they were used for. Permutations are similar, but the difference between the two is what we really want to focus on today. So there's this very not helpful definition of permutation here. I mean, technically that's what a permutation is an arrangement of objects. And specifically, it's an arrangement where taking the same items and reordering them counts as a separate arrangement. So for example, if I was, I don't know, if I was pulling colored cards out of a deck, okay, pulling a red and then a blue and then a green would count as something different than pulling a green and then a red and then a blue. So using the same objects or same letters in a different order counts as a different arrangement. That's going to be the primary difference between permutations and combinations. And you're going to hear us say, order matters with permutations. And it doesn't always have to be like sequencing order, but it's just knowing that this is going to be counted as something different than this. Okay? Okay, so this first example actually should look really similar to some stuff we did in the last lesson, in lesson 7.3. If we've got 8 runners in a race, how many different orders can the 8 runners place? And so we kind of did this. I think there was a horse example where we said, here are the 8 places, right? First, second, third, fourth, and so on. Kind of lost count. Hopefully I did 8. Okay. So there are 8 runners that could come in first. And then once one runner does come in first, there are 7 remaining that could come in second and 6 remaining that could come in third, and all the way down the row. Oh, yeah, okay. And so really we know that that's called 8 factorial, okay? So in our calculator, we can do 8 factorial, and we find out that there are 40,320 ways to place this. In the land of permutations, permutations are always going to be using this notation here. And again, this might look familiar from when we did combinations. But n represents the total number of choices. And r represents the number that we're actually choosing. So, let's see, how do I want to write that? Number being selected. Selected. Sorry, guys. So in this particular problem, I mean, we did this with a factorial, but in the land of permutations, we would say we have 8 choices, and we're placing all 8 of them. So we have 8 runners and 8 positions to put them in, okay? And so if you look in your calculator, I'm going to type that first 8 in that same place I was a second ago under the probability menu. I have this second option that says NPR. So I'm going to choose that. And then I'm going to put the 8 here. And you're going to notice that really is the same as 8 factorial. Okay, because this is essentially what it's doing. But now I want you to look at this one. And how many different ways can first, second, and third place be arranged? So the way we did this before is we said, okay, now we have 3 spaces to work with. I still have 8 choices for first place. I still have 7 choices for second and 6 choices for third. And I could multiply that through manually. So let's see, that's going to be 56 times 6, I think. So this should be 336 ways. Or using permutations, we could say we have 8 runners to choose from, and we're putting them into 3 spots. And in our calculator, we're going to do 8p3. And also comes out to 336. So when I say order matters, what this is doing, what that 336 includes, is if I have, Joe in first place and Steve in second place and Dylan in third place, that counts as a different arrangement than having Dylan in first and Joe in second and Steve in third. So if I take the same 3 runners but rearrange them differently, that needs to count as a new arrangement. So this 336 includes all of those duplicates where I'm taking the same people and just putting them in different spots. And the reason we say that matters is coming in first place is different than coming in third place. But you're going to see some examples later on where if all I'm doing is picking a group of 3 people, it doesn't matter what order I'm choosing them in. And so I wouldn't want to include those as separate arrangements. Okay, there is a formula down here for permutations. You really don't have to know how to do this by hand. This is the formula. If you'd like to write it down, you can. But you won't need to do this by hand. You're always going to be able to do this with your calculator. And I just want to kind of show you what this is doing. So let's think about this 8p3. This is saying we're going to do 8 factorial over an n minus r. That would be like 8 minus 3, so that's going to be over 5 factorial. But what that means is happening here is we have this over 5 factorial. And then all of these are canceling out. So we're left with just the 876 up here on top. So this formula is doing the same thing we just did up here manually, and doing this in your calculator is really enacting this formula. So just wanted you to have a sense of mathematically why that works the way it does. Okay, so example 2 here, and we're going to do less manual work here and more with using our calculator. How many different 4-letter words can be created from the letters in the word equations? So words are any arrangement of 4 letters. They don't have to actually be words here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters to choose from, and I am putting them into groups of 4. So I'm doing 9p4. And I have 3,024 different 4-letter arrangements I could make. And so again, this counts things like if I had E, Q, U, A, and A, U, Q, E. Under a permutation, that would count those as 2 separate arrangements. Even though it's the same 4 letters, they're arranged differently. If all I cared about was how many ways are there to group up 4 letters, then I would be using a combination, which we're going to talk about in just a minute. Okay. Actually, I think we can skip example 3 for now. Yeah. I'll just take that off there for you. Okay. So now we're into that conversation about permutations versus combinations. Does the order of the selected objects matter? And I want to be real careful about how we're using the word order. It's not always like a sequencing order. It's does the position that they're chosen in matter, or are we just concerned with getting a group of the same objects? So when we're doing combinations, we have this formula here, and you'll notice this r factorial in here. What that's doing is removing the duplicates. So just as a quick example here, I'm going to go back to this example 2 that we just did. We did 9p4 and got 3,024. If I did this as a combination, and maybe don't write this down because a combination is not the correct way to do this problem, but 9, and the combinations, if you remember, are under the same place, under that probability. You've got NCR. You're going to find this number is less, right? It's significantly less, because this is saying, hey, these 2 things are really the same thing. Okay, so this particular problem really dealt with permutations, but just wanted you to have a sense of what the combinations are meant to do for you. With combinations, it would count all of those the same. So again, you don't have to worry about knowing the formula. You don't have to do these by hand. Everything's going to be in your calculator. So let's see. Okay. Just want to read my directions here. So we're going to decide if these are combinations or permutations, and then actually do the combination or permutation. So choosing 3 students from a class of 20 to carry textbooks to another classroom. So if I choose, Kayla, Robbie, and Stan, okay, um, it doesn't matter which order I choose them in. There's no ranking here. They're just going to be carrying the textbooks. So it wouldn't matter if I chose them in a different order. All three of them are just going to be carrying textbooks. So this is a combination. I'm going to do 20C3. 20C3 is 1140. Okay. So with this next one, choosing president, vice president, and secretary from student council, well, it's different if, Kelsey's going to be president, Ella's going to be vice president, and Brandon's going to be secretary, let's say. We want to count it as a different arrangement if I choose those same three students but give them different positions, right? That would be a different ordering of people. So it's not so much the order, but the position that these students would be in. We want that to count as something different. So this would be a permutation. I'm going to go 40P3 this time. And again, what this is telling me is how many different, exec boards, if that's what this is, how many different executive boards could I potentially come up with? And again, we're using the permutation because if we chose the same three students but gave them different positions, that would be considered to be a separate board or a new board. Okay, if I'm choosing 6 books on a bookshelf of 10 to take camping with me, well, just choosing 6 books to throw in my bag, it doesn't matter what order they're in, right? If I choose the same 6 books in a different order, they're all still going to the same place. So this would be a combination. So I'm going to go 10C6. And we end up with 210. So there's 210 different ways I could choose my books to go camping with me. Create a 6-digit password from lowercase and uppercase letters and numerical digits. All right, we got a lot of choices here. With a password, does the order of the letters matter? If you choose the same letters but in a different order, does that count as a new password? I would say yeah, it sure does. Okay, so this is going to be a permutation. We have to think about how many choices we have. So if we're doing lowercase and uppercase, that's 52 letter choices total. And numerical digits, there's 10 digits we could choose from. So really we've got 62 different things we can choose. So 62, we're doing a permutation and we're doing a 6-digit password. So we're choosing 6 of them. How many different ways could I make that 6-digit password? This is going to be a pretty huge number, I would guess. Yep, that's a scientific notation number. So we're going to say 4.43 times 10 to the 10th power. Okay, that's pretty giant. By the way, the no repetition of characters is important because this is setting it up so that kind of like that one we started with, like a factorial, where once you put a digit somewhere, you can't use it again. If repetition was allowed, we would technically have 62 choices 6 times in a row. It would really be like 62 to the 6th power, which would actually be bigger than this. Okay, and lining up 10 people for a photograph. So all 10 people are going to be in the photograph. The fact that we're lining them up and rearranging them, I mean, it's the same 10 people no matter what, but we're putting them in different orders. So this would be a permutation. And we're lining up all 10 people. This is kind of like the 8 racers and how many different ways can they place. So 10P10 comes out to be, let's see, 3,628,800. So a lot of these questions really just rely on the wording of the question to understand whether it's a permutation or combination. And we're probably going to have some discussions about some of them because we may disagree on some of them. But that's the idea. When we say order matters for permutations, it really means if I take the same objects and rearrange them within themselves, do I want that to count as a new arrangement or not? And sometimes, like with positions, president, vice president, and secretary, I do want that to count. But if I'm just choosing 3 students to go do the same thing, there's no difference between those 3 students. It doesn't matter which order I call their names. So that would be a combination. So you're going to practice some of these tonight. We're going to continue practicing them for the next couple of days, but just so you know what this is really heading into is we're going to loop back into probability, but this is going to help us figure out, how many different outcomes are there that we like and how many different total outcomes could there be. So if I wanted to know what's the probability that, these two books end up going with me here, this would be like my total number of possibilities, and I would set up a fraction out of 210. So we will eventually kind of divert back into probability with this. Right now, we're still just focused on how do we find the total number of combinations and outcomes. Okay, that's really it. I'm sure we'll be talking about these more in class, and I'll see you next time.